Hey everybody, Mr. Ellinger, and here's the second Lagrange problem. And so I've already written some stuff down just to kind of save myself some time later on. So let f of x is equal to this, and in essence we're going to be making a Taylor series for this, but we're going to be doing it in an unusual way. So it says first write the first four non-zero terms for the Taylor series for sine x. And so it says the first four non-zero terms. So I just did the first four terms here. I hadn't seen the non-zero yet, but that's an important observation. And so if I was writing this, then I'd say sine of x is about equal to 0 plus 1x plus 0 over 2 factorial x squared plus negative 1 over 3 factorial x to the third. Oops, just complete that 3. That's a terrible 3. That's homely. Okay, no offense. All right, so, and I'd be thinking, oh, I'm done, but it's a non-zero term, so these ones don't count. So I'd have to keep going, but I can see the pattern, and I can see what's going on here. And eventually, this will be one that we just have memorized. And so it's just x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Part A, first part is done. And then it says write the first four non-zero terms of the Taylor series for sine x squared about x equals 0. And you might say, oh man, we're going to have to do some derivatives and some chain rules, and this is going to take us a while. And but it actually isn't, because sine x is about equal to this thing. That means that if I want to find sine of anything, I can just plug it in. Well, let's find it sine of x squared. Well, that's about equal to, and I plug in x squareds for all the x. Sweet! So it's x squared. I mean, it's just easy, right? Like a lot better than doing the Taylor series from scratch. So that's 6. Plug in x squared and then 2 to the 5th. So that's x to the 10th over 5 factorial, and then minus x to the 14th over 7 factorial. X to the 14th, wow. I don't know if I've ever had to have an x to the 14th, like legitimately in a problem. Okay, I mean, like 14th, x to the 14th, that's huge. All right, so question B. Right, so that's A. Whoops, A. That's the first part. Question, the second part. They always divide them up, but I didn't divide it up for you. Question B. Write the first four terms of cosine x. Okay, so here's my derivatives. So cosine x is equal to non-zero terms again, not about equal to 1 plus 0x. Okay, I don't need that, so I go straight to minus 1 over 2 factorial x squared plus, and then it'd be the fourth, so 1 over 4 factorial x to the fourth. Oh, I got it. Minus 1 over 6 factorial x to the sixth. So let me just rewrite that. So it's 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the 6th over 6 factorial. Done. Next question. And now use this and the series for sine of x squared found in part A to write the first four non-zero terms of the Taylor series. Okay. Well, all right, so I'm adding these two functions together. I've got this one and I've got this one. Okay, cool. So the first four non-zero terms for sine of x squared plus cosine x has to be about the sum of those two functions. Well, the first term is going to be a 1. And then the second term, I've got an x squared, and then but I've got a minus x squared over 2, so that'd be plus x squared over 2. Right? Because that's 2 factorial is just 2, so it's x squared minus 1/2 x squared, so that'd be 1/2 x squared. Okay. And the next one is the x to the fourth, and it doesn't have a partner, so it's good. 4th over 4 factorial, and then the next one. Okay, so I've got a minus x to the 6th over 3 factorial, and then I've got a minus x to the 6th over 6 factorial. So 3 factorial is 6, and 6 factorial is a big number. Just doing a double check on this. First four non-zero terms. Okay, so x to the 6th is 720, and so it's 1/6 plus 1 over 720. I'm combining this, and this. And so it's a minus x to the 6th, but what's the coefficient? Oh, okay. So I need to multiply the top and bottom of this by 1. So it's 121 over 720. All right, I'm putting it down. I'm not feeling great about that, but this is a short video, and x is 6. There we go. Done. Okay, now it says find the value of f6 of 0. So I want you to think about this for a moment. Like the 6th derivative of this. So the 6th derivative of this thing, that's going to be tricky. I mean, the cosine's going to be easy, but I'm going to get product rule. I'm going to have to do a bunch of stuff with that. I could try to read it from the graph, and it looks like it might be undefined, actually, looking at it from the graph, but I'm not sure about that. And the scale here is kind of wacky. And so I'm trying to figure out, like, how would I possibly figure this out? Aha, there's a way. This coefficient right here, see, negative 121 over 720 is taking that part of the Taylor series. So this thing represents f is f6 of 0 over 6 factorial, because that would be the coefficient for x to the 6th. So this is where it starts getting kind of interesting. It's like, oh, now I'm using a series that I've created to tell me stuff about the function that I didn't know otherwise. You might be like, well, this looks really bad, Mr. Ellinger. No, it's not, because 6 factorial is just 720, and I multiply both sides by 720, I get f6 of 0 is negative 121. That easy peasy. Okay, this is a lot of just series stuff, and that part of it does not have to do with Lagrange, but I wanted to show you that anyway. And now the next one. Let P4 be the 4th degree Taylor polynomial for f about x equals 0. So it's just the 4th degree one. And so the 4th degree one is just stopping right here. Right? So the 4th degree is that. Using information from the graph above, show that P4 of 1/4. So the Taylor degree polynomial for 4th. So they used P4. Sometimes people use T4. I've seen both. So P4 of 1/4 minus f of 1/4 has to be less than 1 over 300. So whenever you see that absolute value and the subtraction, you're going, okay, this is an error thing. And we're doing it from a Taylor polynomial, so this is the Taylor polynomial. This is the Lagrange error bound. So what do we know is true? Well, we know that if we stop at this 1 plus x squared over 2 plus x to the 4th over 4 factorial, and we stop there, then the next term is going to be, the next term in a Taylor polynomial is going to be plus f5 of 0 x to the 5th over 5 factorial. Okay? But you might notice that, wait, there isn't a 5 factorial in here. I don't see a fifth, I don't see an x to the 5th in here. Well, the reason why is for the Lagrange error bound, we don't put in 0 into this. We're going to put in some number z. And this is our error, evaluated at some value of z. Okay, so that error is the 5th derivative of z, a 5th derivative evaluated at z over 5 factorial, that's 120, times x to the 5th. Well, I'm approximating it at 1/4. So it's times 1/4 to the 5th. Okay, so now the question is, this is what the error is. What's the worst that this could be? So the max error. Well, what's the biggest this number could be here? Right? I mean, that's the biggest question. What's the 5th derivative of z? What could it possibly be? And so we can go back to the graph they gave us. They actually gave that for a reason. This is the fifth derivative of f, and that's why I need it for this. But I love this problem because they did a great job of asking it. That some people say, well, is the biggest value of f right here? Of the fifth derivative of f, is it there? Is the biggest value up here? What's the biggest value? And the big thing about Lagrange error bound is that z has to be between C, which is the center of your expansion, and X, which is the value you're approximating the function at. So in this case, since 0 was the expansion, center of the expansion, it's just a Maclaurin series. We didn't do it around anything else. We did it around 0. And X is 1/4. How do I know that? Because we're estimating the error when you plug in 1/4 into the function. And so Z has to be a number between 0 and 1/4. All right, let's look at that. Oh, here's 1. So here's a half, here's 1/4. So the worst possible value, the biggest possible error would be at this thing right here. Well, I don't know what that number is, but I know it's less than 40. So the maximum error, I have to say that F5 of Z has to be less than 40. And I could kind of approximate it. I could say it looks like it's about 30, maybe a little over 30. So maybe I'd go 35 or something. I'm just going to leave it at 40. Okay? So that's the worst that part of the error could be. And so the maximum possible error is 40 over 120. Like, because the worst this could be is this could be 40. Like, that's the biggest error that we could get, or the biggest contributor to the error, to the fifth. Okay, well, what is this? Well, this is 1/3 times 1/4 to the fifth. So 4, 8, 16 times 4 is 32. 64 times 4 is 128. 256 times 4 is 1024. So times 1 over 1024. So the max error actually has to be less than 1 over 3072. Or I should say that the error is definitely going to be between less than 3,000, 1 over 3072, and they asked to show it that it was less than 1 over 3,000. And check over and all right, so what did this problem show? 12.5. Okay, I'm doing pretty good. So neat problem. This is a question 6. This is probably a pretty tough question 6, would be my guess. We'll look at the data in just a second. See how people did. So what did we have to do? We had to know how to expand sine x using the Taylor formula, and we're gonna have a shortcut for this. Sine is one that we're just gonna memorize, to be honest. And then we had to find sine of x squared. Well, we could just plug x squared into sine x, and so that was actually really easy. Then we created our Taylor series for cosine, and we did that using the Taylor formula. But that is actually another one that we're just going to memorize, not a shocker. And then it asked us for the first 4 non-zero terms when you combine these two together. And so I was just grabbing terms of low degree. So 1 was the lowest degree, and then x squared was the next one, and then there was an x to the 4th, and then there was an x to the 6th, and an x to 6th, and x to 6th, and I stopped there because that was the first 4 non-zero terms. And that was the answer. So now in C, they asked us, what's the 6th derivative of f at 0? And we realized we have the 6th derivative term there, and we know that this expression in the Taylor series is f6 of 0 over 6 factorial x to the 6th. So that number right there, negative 121, is the 6th derivative of f at 0. And we didn't have to do any work. And finally, the last question was about the Lagrange error bound, and this is part D. And the big thing is that the error is going to be less than the next term in the series, in the Taylor series, which was kind of weird because it was 0. There wasn't an x to the 5th term, but then I realized, oh, wait a minute, we're not going to plug 0 into this thing. That would make it 0. Instead, we're going to plug in some number between 0 and 1/4, and that's what makes the error possible. We'll be doing more with Lagrange error bound and all kinds of series stuff. I will tell you, that is the most complex idea of the year. You're done with it. You're done with the hardest idea of the year. And it's smooth sailing from now in. I mean, it's going to be challenging at times, but this is the toughest thing. So give it some time. We're going to keep cranking on Lagrange and be learning some more stuff. And I will see you tomorrow, late start. Bye-bye.